So building on the work we did last time with maximums, minimums, and finding critical numbers, we're to a couple of theorems and a method for finding absolute mins and maxes. So the theorem is that if f has a local maximum at c, then c is a critical number of f. So this is important for us to remember here. We saw this in the last sort of video, that critical numbers tell us information about these local mins and maxes. And here we're just formalizing that. And now, because of that, because we can put that together and for the following. So the closed interval method is what this is called. And the problem that we're trying to solve with this is to find the absolute minimum and maximum values of a continuous function f on some closed interval a to b. And we have a very nice method of doing it. So first we find the critical numbers, and then we find the values of those critical numbers. Then we find the values at the endpoints, and the largest of these is going to be the max, and the smallest is going to be the min. So as long as you've got some continuous function a to b, and it doesn't matter what the function might be, if it's something like this, continuous, the point is the absolute mins and maxes are either going to occur at the endpoints or they are going to happen at some critical numbers, at some local min or max. And those are the only possibilities. So we don't have to look at every value. We only have to look at these very specific values in order to determine the absolute min and max on an interval. So let's go ahead and do an example here. So f of t is this function here, t over t squared minus t plus 1. Now, if we're going to start this off, we need to start by finding the critical number. So we need to take the derivative and set it equal to 0 and find the critical numbers. So we'll take low times the derivative of the top, which is just going to be 1, minus the top times the derivative of the bottom. So we get 2t minus 1 there. And then we're going to have t squared minus t plus 1 quantity squared. And if we go ahead and let's clean this up a little, t squared minus t plus 1. And then we'll have minus 2t squared plus t. And t squared minus t plus 1 squared. And so what we get is negative t squared plus 1 over t squared minus t plus 1 quantity squared. Now to find the critical numbers, either the numerator is 0 or the denominator is going to be 0, because that would give us this undefined bit. So let's go ahead and do those two things separately and try to solve that. So if the numerator is equal to 0, we'd have negative t squared plus 1 is equal to 0. And so if we add t squared to both sides, we get 1 is equal to t squared. So t is going to equal plus or minus 1. So there are two critical values. And we want to know, is the denominator ever equal to 0? And so we can go ahead and look at that. And if we look at this, we actually know that this is going to have no solutions, because if we look at the discriminant of it, b squared minus 4ac, that part that comes underneath the radical, we get that this is 1 minus 4 times 1, which is negative 3. So underneath the radical, we're going to have a negative 3. So this is going to have no real solutions. So our only critical numbers are plus or minus 1 here. So now for the other parts, so for find the values of f at the critical number. So what I really want to plug those values into the function and find the value. And I'm also going to want to do that for the endpoints of the interval here. So let's just do all of that at once. So what I need to find is f of 0, and I'm getting f of 0 from up here, that one endpoint. I have, here's a good point. So this t equals negative 1 that we got as a critical number, I don't actually need to worry about, because -1 is not in this interval, right? So I then just need to check f of 1, because that actually is in the interval. And then lastly, I need to check f of 3. So if we plug those values into the function up here, when we plug in 0, we will get 0 as our answer. When we plug in 1, we will get 1 as our answer. And when we plug in 3, we will get 3 over 7. And again, I'm just plugging those that up in. I'm plugging f of 0 in, so I'm plugging 0 in for t and evaluating here. And so what I can get from this is that my maximum at this is at the point 1, 1, and our absolute minimum occurs at 0, 0. And let's go ahead and check this against Desmos. So as we look here, this is what the graph looks like, but we are only really interested in the interval from 0 to 3. So let's zoom in there and look at that. And let's actually just label these points: 0, 0, f of 0, 1, f of 1, and 3, f of 3. And we get these 3 points here, and we see that it is, as we suggested, that the absolute minimum occurs at 0, 0, and the absolute max occurs at 1, 1. Now let's try this next example where g of x is equal to x minus 2 times the arctangent of x from 0 to 4. And remember, arctan is another way to write tangent inverse. Maybe you want to hit pause here and try to do this on your own. So part 1, we want to take the derivative of this function. So we get 1 minus 2. And then the derivative of arctan is 1 plus x squared. So if we wanted to get a common denominator here, we'd have 1 plus x squared, and then we'd have 1 plus x squared minus 2, which becomes x squared minus 1 over x squared plus 1. So if we want to go ahead and solve this, we are never going to get the denominator is equal to 0. This is always going to be positive. So I really just have to worry about when is the numerator going to equal 0. And again, we are going to get x squared equals 1. So x has got to equal plus or minus 1 in this case. So in a very similar way to what we had in the last example, we have g of 0 that we need to check. We need to check g of 1. We don't need to do the minus 1 because it doesn't fall in our interval up here, and we need to know g of 4. And I'm not using a calculator here. I won't until I need to. So when I plug 0 into my function, I get 2 times arctan of 0, which is actually just 0. So g of 0 is equal to 0. G of 1, I'm going to get 1 minus 2 times arctan of 1. And arctan of 1, you might remember, is pi over 4. So this is 1 minus 2 times pi over 4. And so this is 1 minus pi over 2. And then g of 4 will be 4 minus 2 times arctan of 4. Now, we could use a calculator to, approximate these. You actually, if you have worked with these functions enough, you don't really need to. If you look at this, you know a couple of things. You know that this number here, 1 minus pi over 2, is going to be negative because pi over 2 is about 1.5. So 1 minus 1.5 is going to be something that's negative. So we know that. And then this g of 4, well, arctan of 4, arctan is never bigger than pi over 2. So even at its worst, if this was around pi over 2, this would be 2 times pi over 2. So this would be like 4 minus pi at worst. So that's going to be positive. If you're not happy with that analysis, you are welcome to get out a calculator, but it is a useful thing to be able to work with these numbers this way and have some sort of number sense for numbers involving pi and tangents and things like this. So if I go ahead and, plug this into a calculator, this is about negative 0.57. And if I do the same thing with arctangent, this is about 1.35. So we do know where our mins and maxes are going to be. So this says our absolute max is occurring at 4 and 1.35. And at least we're just really talking locally. We're on this interval. We're not doing it for every value, just on the interval here. And then along the same lines, absolute minimum on this interval is going to be at 1 and about negative 0.57 here. Let's go ahead and look at the graph. So if we look at our graph here, we've got our endpoints at 0, 0 and at 4 here, and our one critical number we found, which was around negative 1. We get an answer that coincides with the calculus that we just did.